All right, so we're going to look at number 11 from the homework. I've seen problems like this where you're um, trying to, this one's where I think a pipeline is being laid, oil pipeline, to go from the, I guess, the oil rig in the ocean to the refinery on the coast, correct? And what does it say? It says that when you lay the pipe, it's twice as expensive in the ocean. Okay, so of course the length that you lay the pipe is gonna, have an effect. So it's usually like, what would the cost be? Like something per foot. Okay, so whatever, and it says that it's twice as much to lay pipe in the ocean as it is to land. So let's look at the extreme scenarios for laying the pipe. One is, the shortest distance will be from the oil rig straight to the refinery, this here, from here to here. That's the shortest distance, but the problem with that, and we'll just draw this in blue, is if we take this path here, yes, we're not using as much pipe, but it's going to be very expensive because whatever that length is, it's twice as expensive as what we would normally do on land. All right? So that would be an extreme scenario. We probably don't want to take that route, okay? The calculus will show us what route we're going to take in a second. Now, if it's cheaper on land, the quickest way to get to land is to go straight down here and then go straight down the shoreline, okay? Well, this is going to be cheap for us to lay that pipe, but look at how long that is. It's a long distance because we're basically using the two legs of this right triangle as you look at it. So the distance is too long. So the first thing we're going to do is we know that there's the optimal path, and that's what we're looking for. We're trying to minimize our cost. Now, before I get to that, my cost is going to depend on the length of the pipe. So I'm going to write what the length is, and then I'll come up with my cost equation from there. So I can see that there's some arbitrary point down the coast from this perpendicular distance here, that this is X units, whatever that is. That's where we want to hit land, and then from there we'll go on land to the refinery. So that way it's cheaper here. So what I'm going to do is I'm going to call this length 1 and this length 2 and write out my two lengths. Okay? So now let's look at what we've labeled. So we've kind of drawn, they have the figure drawn for us anyways. I think they went ahead and called that X. What did they tell you that this was right here?
6 minus.
Yeah, does it make sense that this is 6 minus X? If all that's 6 and you take away X. So you've already got L2. The length 2 is 6 minus X. And X is what we don't know. It's not constant, right? We're trying to move X to see how's it going to affect our cost. All right, L1, if you notice here, if you look at this figure, we got a right triangle with X4 and X. So we can solve for L1 just using Pythagorean theorem. So we can see that L1 squared equals 4 squared plus X squared. So L1 squared is 16 and X squared. So L1 is the square root of 16 plus X squared. So there's L1. So the total length is L1 plus L2, but that's not my cost. Okay, so what does it say? It says it's twice as expensive than what it is on land. So I don't know what it is to lay the pipe on land. So what I'm going to say is the cost on land is K dollars, not land per foot. I think the problem is in feet, or is it in miles, or what is the?
I think it's kilometers.
Kilometers, K dollars per kilometer. Okay, so we'll say that the cost on land is K dollars. We don't know what it is. $10 per kilometer. We know it's not $10 to put an oil pipe there, but whatever, K dollars. So therefore, the cost in water is going to be $2K per kilometer. Okay? So I'll just double whatever this one is, I double that. And so now I have to know how many kilometers, which that's what these lengths represent. These represent distances. So if I take this distance and I multiply by this cost, that should tell me the cost to put it into water, and that should tell me the cost to put it on land. So my cost equation is gonna take my two lengths and multiply them by their price. So the length one is gonna be 2K times that. Because this might be 3 kilometers, then whatever the cost per kilometer is, we multiply. And then the cost for L2 is K times L2, okay? Because L2 is on the land, L1 is in the water. And then we know what L1 and L2 are, so my cost equation is 2K times square root of 16 plus X squared plus K times 6 minus X. And there is my cost equation, and K is just an arbitrary, just a constant that represents the price. You could have used $1 and $2. The K, as you're gonna see, is gonna be insignificant. We're gonna end up getting rid of the K. All right, so this took a little work because I had to not only do I had to first think about the lengths, and then I gotta think, well, how's cost? Cost is gonna be dependent on those lengths. And so we wanna minimize this equation. So now we're okay. You're gonna say, well, I have a K here. K, I can tell you, you can leave it alone because think, what's gonna end up happening? When you take your derivative, you set your derivative equal to what? When you do maxes and mins, you take your derivative, you set your derivative equal to 0. And you're gonna get rid of your K. It's a constant. First thing you do is divide by K. So what I'll do is I'll just factor out a K. All right, there's that. And now I'll take the derivative. So K is factored out 2 times. Derivative of a square root is the derivative of the inside over 2 square root. Plus derivative of 6 minus X is -1. All right. Okay, so then we're gonna end up setting this equal to 0 here in just a second. Now, let's do this. Yeah, I can cancel these 2's. I cannot find a marker I'm happy with. Try again. And so we get our C prime is K, here we go. 2x over square root of 16 plus X squared minus 1, and we're gonna set that equal to 0. Because you're not worried about the bottom being 0 because 16 plus X squared cannot be 0. Okay. All right, there we go. There's that. Nice. That's a lot better. It shows up a lot better. Okay. So now how do I go about solving this equation? Okay. So what I'm going to do, first thing, now my K is insignificant. So since I set it equal to 0, I divide both sides by whatever that was. But you really, the way it came into play was to have this doubling factor here. When you put 2 times this, that's what's important. If you don't have that 2 there, it's going to throw off your answers. Okay. Now remember what I said, when I do derivative, I don't like to leave separate fractions. I would get a common denominator of the square root of 16 plus X squared and make it into one fraction. So this is going to be 2x minus, so this is square root of 16 plus X squared minus square root of 16 plus X squared over square root of 16 plus X squared, because I get a common denominator equal to 0. And the only way now, I'll make it one fraction. So I have, just know that we're up here, 2x minus square root of 16 plus X squared over square root of 16 plus X squared equals 0. The only way that that fraction can equal 0 is if the top is equal to 0. The bottom can, you don't, that's not how a fraction equals 0. The bottom makes it undefined, but you can see the bottom can never be 0 because you have 16 plus a square. It's not going to be 0. So I'll take my numerator, set it equal to 0, and this is what you must solve to find your critical numbers. Now, the easiest way to do this, to solve this one, is notice you have a square root. We typically, and our x is in a square root. So what would we like to do to a square root? so that we get rid, what do you normally do to a square root to get rid of it? Square it, so I'm just gonna move it on the other side, like this. So now, if I can square both sides, I'll eliminate that square root, okay? And so I get 4x squared equals 16 plus x squared. And now I can solve, because I have both our x squared terms. Subtract x squared, 3x squared equals 16. X squared is 16 thirds. So x is the square root of 16 thirds. You don't want a minus because you're not going to go in a negative direction. And if you take the square root of the top and bottom, you get 4 over square root of 3. Now we should go and make sure that that minimizes our cost. So here's your, wherever you want to use this fraction here, you could, and 4 over the square root of 3, whatever that value is, you probably want to use your calculator. X is not going to be smaller than 0, and x is not going to be bigger than 6. So 4 over square root of 3 should be something like 1 should be in here. 4 over the square root of 3 should be, well, can you type it in real quick? Tell us what 4 over square root of 3 is. I think it's like a little bit bigger than 2.
2.31.
2.31. All right, so we'll come back to that. So I would test 1 and 3, just to make sure that it is a minimum. So let's see, if I plug in a 1, I get, so if we go to here, this is an easy one to plug into. 2 minus square root of 17 over a positive, right? So if I plug in a 1, I get 2 minus the square root of 17 over a positive. Well, 2 minus the square root of 17 is negative, so decreasing. And then if I plug in a 3, I get 6 minus the square root of 19. I'm sorry, 6 minus the square root of, if I plug in a 3, of 25, because it's 16 plus 9. All over, it's a positive, doesn't matter. Well, that's 5. 6 minus 5 is 1. We get a positive answer. So it was a minimum. So there you go. 4 over square root of 3, which you said is approximately 2.31. So that tells us how far down the coast to go. So if we go 4 over square root of 3 kilometers down the coast, and that's where we put our junction there, that will minimize the cost. You can't see where this would be an important, because we're talking millions of dollars. You can't just play around with that, right? If you're hired to help the oil, if you're working for an oil company, you should be making a lot of money, which would be nice, but you've got big decisions to make there, right? So that's it. Okay, that's that one. All right, what was the, so this one is filmed, you can go back, look at it, see if there's parts that you don't follow. What was the next one, the Norman window? Yeah. Is that one you'd like to look at? Just maybe the algebra on it? What number is that? 15, okay, so let's look at number 15. All right, and help me with the markings and just make sure I get everything correct. So I think, I mean, this is a Norman window. It's rectangular on the bottom. I'm pretty sure it's rectangular and not square. It could be square. We'll see what you tell me. And it's a semicircle on top. And I believe that this length is X, and they call this Y, correct? Is that correct? Yes or no? X by Y?
Yeah.
Yeah, so therefore the radius of this semicircle is X over 2, which you would have that. All right, what else am I missing? What other information is there in the problem? The perimeter, maybe?
Yeah.
What does it say?
Mine's 22 feet.
All right, let's just use that, because they all could be a little different. So your perimeter is 22 feet? And what does it say? What are the dimensions used to maximize the area of the Norman window? Is that the question? What dimensions must be used to maximize the area of the Norman window. Okay. So I know what I want to maximize. Very simple, area. So I got to write out the area of this window. So notice it's a rectangle plus a semicircle. So I know that my area is what I want to maximize. And I'm going to find the area of a rectangle plus the semicircle. Okay? And that's going to be what I want to maximize. All right? So the rectangle is fairly simple. What's the area of the rectangle? XY. All right? Plus, what's the area of a circle? Just a total circle.
Pi r squared.
Pi r squared. But we have half a circle, so I'm going to say 1/2 pi r squared. So notice, I'm just putting the formulas and I'll go and replace everything. So remember in the recipe when I gave you this, when you write out your equation of what you want to maximize, make sure you're in terms of how many variables? One. Only one variable on the right, okay? So I'm going to have to get rid of this y somehow, and I'm going to have to get rid of the r. Well, the r is easy, because since this dimension here is x, thus half of x will serve as the radius of this semicircle. So I'll go ahead and take radius out and put in x over 2. And then I'll go ahead and square that. So now I have x by y plus 1/2 pi x squared over 4. So I have x by y plus pi x squared over 8 if I multiply. All right, better, but my area is still now in terms of x's and y's, so I got to get rid of the y. But that's now where this other bit of information comes in, that the perimeter is 22. And so perimeter is, you would not count this middle as perimeter. Perimeter is here, 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 and around the circle. So let's see. So this is x, that's y, and then we got to do the distance around. So for my perimeter, so I need another equation because what the problem is, I have two variables on the right hand side. So perimeter is y and x, so 2y plus x, plus this circumference here, and it's half of a circumference, so 1/2 of a circumference. And circumference of a circle is 2 pi r. Okay. And that perimeter should equal to 22. So now I'm going to solve for y in terms of x, because I don't want, I don't want to have two separate variables on the right hand side. I got to take this r out again, so radius again is x over 2. So that goes in for radius right there. Okay, so now let's start making whatever simplifications we can. So I would cancel these two x's. So I have 2y plus x plus pi x times 1/2, which is over 2, equals 22. And I'm going to just move these two to the right hand side and divide everything by 2, and that's my y. Okay. Any questions on what I've done? So this is the perimeter of the rectangle. Notice you don't use this central part because it just wants the perimeter of the window. And this is the circumference of a circle is 2 pi r, but I multiplied by 1/2. So I'll just bring these two over. So 2y equals 22 minus x minus pi x over 2. And then if I divide everything by 2, that's my y. Not pretty. Okay. So my y is 11 minus x over 2 minus pi x over 4. Because all I did, divide each piece by 2. 22 over 2 is 11. X over 2, pi x over 2 divided by 2 is pi x over 4. And that goes in place of y. So area equals x times y, which is 11 minus x over 2 minus pi x over 4 plus pi x squared over 8. Now my area, not pretty, but it's in terms of one variable. What I remember on this problem is that the algebra can get very bad, okay? So we'll leave this here, okay? So we did rectangle plus a semicircle. So notice how I started in the simplest form. What's the area of my window? It's a rectangle and it's a semicircle. What's the area of a rectangle? There's that. What's the area of a semicircle? There's that. And then I start slowly replacing. I think it's important to see the work like that so that I can see, keep everything organized, because as you can see, the algebra can get bad. Okay, I'll ask you. So now we have our area equation all in terms of one variable. What do you think would be best to do next? Okay, good suggestion. I would distribute the x, and then I would combine like terms, right? It's got an x times. So I'll distribute the x. See, now you're going to see you got two like terms you can combine, especially with these, what do you call it, the pi's, see? So now, since I have a pi x squared over 4 and a pi x squared over 8, I'll get a common denominator and make these two one term, because those are like. Those are both pi x squares, okay? So I'll multiply this guy by 2 over 2. So I have area equals 11x minus x squared over 2 minus 2 pi, and pi is minus pi x squared over 8. Okay, and you could make it one fraction if you want. It's not going to matter because it's going to be a linear equation when we go to solve. Okay? Any questions on any of the work at this point? Now, I'm pretty good here. I'm going to go ahead and find my derivative. It's 11 minus 2x over 2 minus 2 pi x over 8. Okay? And we're going to set that equal to 0. All right. Now let's see. What should we do? How should we do this? Well, remember what I said about making one fraction. Usually I like to have one fraction. So what I would do, probably not cancel these twos. I'm just going to make this 8x over 8 and make that 88 over 8 so that I have an 8. Well, dang it. Here, hang on. Let's rewind. Reduce that down to a 4. So that's pi x over 4. That's going to be 4x over 4. That's going to be 44 over 4. So I got 44 minus 4x minus pi x all over 8. I'm sorry, all over 4 equals 0. So I got a common denominator. All right. Now, how's the only way that fraction can be 0? How's the only way a fraction can equal 0? What part of the fraction has to be 0? The top, the numerator. The denominator cannot be 0. And even if the denominator is 0, it's not 0, it's undefined, but the denominator cannot be 0. So the only way that I can solve this is if I see what makes the top equal to 0. So the 4 is insignificant here. I could just multiply both sides by 4 and it's gone. So now 44 minus 4x minus pi x is 0. And now what I would do is I'm going to get my x's on one side. So leave the 44 here, move the x's over so they both become positive. And you're gonna say, well, how do I combine a 4x and a pi x? Just factor out an x. So if I factor out an x, I'm left with 4 plus pi times x. And then that's it, divide by 4 plus pi. And that should be your x dimension for the window. Oops, 4 plus pi. So x equals 44 over 4 plus pi. Now, you're gonna say, well, how do we know that, let me go back to my a prime. A prime was 11 minus 2x over 2 minus 2 pi x over 8. So you're gonna say, well, how do we know that this gives a maximum? I'm gonna use second derivative test from 3.4. So I'm gonna real quick find my second derivative, which I would get, 11's gone. Negative 2x over 2 is just, I mean, that's just negative x, so that's just negative 1. And this is minus pi over 4. So notice that my second derivative, the x's are gone. All I get is negative. So if my second derivative is negative, that means my graph is concave down. So if that's the critical number, then that has to be the peak. So that's a maximum. Okay? All right, there's that. Now, it said probably in the start of the problem, give the x and y dimension. So now here's where this is a bit of a pain. You got to go back to y, which is this. And guess what you got to do? You got to sub in x. So y is 11 minus this, 44 over 4 plus pi over 2. So I'm going to my y and subbing in for x. Minus pi over 4 times x, which is 44 plus pi over, what did I mess up? 44 over 4 plus pi. Ooh. So, looks bad, but I'll do a couple of hints here. So what I would do, leave the 11 alone for now. This 2 will go into 44, make that 22. So I get minus 22 over 4 plus pi. And then over here, I can cancel 4 into 44. That leaves 11, so minus 11 pi over 4 plus pi. And then all I would do, make a common denominator of 4 plus pi and make the combine the numerator, and I should get an answer there. All right, so I'll do the algebra. You can catch up to this later. So for y, I got 11, see if you can, yeah, times 4 plus pi over 4 plus pi minus 22 over 4 plus pi minus 11 pi over 4 plus pi. So I'll have to go up here and do my work. So I have 44 plus 11 pi minus 22 minus 11 pi all over 4 plus pi. Well, that works out nicely. 11 pi's cancel, and I'm left with 22 over 4 plus pi. And there's my y, and there's my x. And there's the algebra that goes with it. And that's why I said this problem is difficult, because of the algebra. You can see the board, how much it takes to work a problem. Now, granted, we could have gone back to here and done the whole problem how? If you want to maximize area, how can you do it graphically?
Just plug it in.
Plug it into your calculator, graph it. What are you looking for if you're looking for a maximum? The peak. Find the peak. That's it. So you could have stopped here if you had your calculator. But in the AP exam, what you're going to take at the end of the year, end of the school year, is half calculator, half no calculator. So you don't know what you have at your disposal. But you could have saved yourself some of the math. Okay. Let's do one more problem. What was it? The line in the square, maximize or minimize the area of the square, something like that. Let's do that one. Hey, do you have the answers? Are you checking? Yeah, so those look familiar to me, by the way. But this is not my first rodeo with this problem. It's a famous one. Okay, let's do one more problem. There should be a line and a square. What number was that? 16, okay, we'll get one more. Okay. And just give us the one that it has on yours. What's the equation of the line? And so this line would be here, here, and you have some rectangle in here, right? And what are we trying to do with that rectangle? What does it say? Maximize the area of the rectangle. Okay, well, all right, so good. So we want to maximize area. So we're trying to find this rectangle in here. We don't know where it hits, right? We can see the further right we go, and so this top corner has to touch the line, not go past it, right? So I don't know the dimension, so I'm going to call this dimension what? X. I'm going to call this dimension what? Y. There's that. So do I know my area of my rectangle right now? XY. So notice, maximize area of the rectangle. So now I write out area of the rectangle, XY. Notice how I start simple with words, then with an equation. But what's the problem? I can't have two variables. Now what's nice about this? The nice people in the problem gave me y. Y is what? 6 minus x over 2. So what do I do here? I go over to my y, I take it out, 6 minus x over 2, and now I have the area in terms of one variable, and that's it. So I would write this, I would have written this 3 minus x over 2, right? If I divide both of these by 2, then I can distribute my x, makes it a little bit more attractive. 3x minus x squared over 2. So all I did is I changed this line to 3 minus x over 2. So that way it would much be easier to differentiate. And then I find the derivative. A prime, 3 minus 2x over 2, which is 3 minus x. Okay. Set that equal to 0. X is 3. Now, how do we know that that's the location that's going to give us a maximum? And I didn't mean to do that, but it worked out that way. 1, 2, 3. Because I just kind of eyeballed where I thought the rectangle should go. All right. How do I know that this gives us a max? I'm going to, instead of using first derivative test, I'm going to use second derivative because it's going to take me 2 seconds to find the second derivative. Since a prime is 3 minus x, a double prime is -1. -1, since the second derivative is always negative, the graph is always concave down, which makes sense because it's a downward parabola. Thus, that critical number is a max. So if x is 3, y is what? Well, you can plug in and get your y, you're going to get 3/2. 6 minus 3 over 2, y is 3x. Did it want the area or did it just want the coordinates? Coordinates. So when x is 3, which is what I had drawn here, just worked out that way, y should be 3/2. So in terms of the difficulty, we would rank this on the much simpler end, correct? Not as bad as the other ones. All right, there was 3 problems from your work. We'll pause there. I think that gives you plenty of stuff to look